Hello everyone, this is our project on the Smart Solar Power Collector. Our team is Windy City Solar Company, and I'm Shane Russell and my partner is Daniel Cass. This is our outline representing our slideshow. The things that stood out to us about solar collection were the inefficiencies around residential use. We quickly realized the limits of residential solar energy. Efficiency is at its greatest when the panel is focused directly at the sun. We plan on using our knowledge from computer and electrical engineering to solve the problem by implementing a solution that is more efficient than standard solar panels used on most residential buildings.
The popularity of solar panels is on the rise due to the environmental advantages they create. Some of these advantages include being a renewable energy source, having a very small impact on the environment, and having lower water requirements than other energy sources such as nuclear and coal-based energy. Solar panels have been around since the early part of the 20th century. A more rigorous application of solar panels took place in the 1970s when traditional energy source costs began to rise. Solar panels are now common in residential, commercial, and industrial use. The left picture displays modern solar panels in commercial use. The right picture displays modern solar panels in residential use.
Our current needs revolve around emergency use such as natural disasters and emergency power stations, power loss for systems such as auxiliary backups, off-grid power for essential water pumps, and electrical components such as lights.
Solar power utilization will decrease the use of fossil fuels, which inherently reduces emissions of carbon dioxide and other gases responsible for the greenhouse effect.
Solar panels are typically large in utility use. The potential for catastrophic failure is very low, but always a possibility over time. Fossil fuels are still used in lubricants that are required to grease moving parts.
These are standards relating to solar power generation. A link is available at the end of the presentation to view these requirements in depth.
With our requirements, the final system must come in with a budget under $2,000. The system must provide consistent power and be able to provide emergency power during a grid outage. The final system needs to maintain a low maintenance profile and must be easy for our company to reproduce, utilizing non-agricultural real estate, as well as reducing the needed size for a solar farm due to the efficiency gain of motorized solar panels are benefits of this design.
The engineering requirements for this system are that it must have a higher efficiency rating than static solar panels, must use a Distech ECY VAV controller, must be easily deployable, must use 4 100 kilo ohm photovoltaic resistors, and must track the sun's position without any human interference.
Keeping a solar panel in the optimal position during sunlight hours is a major benefit due to static solar panels losing their efficiency of over 20% daily. The efficiency increase is very appealing with a 2-axis system.
The objective tree is a great display of the goals at hand for a project. Here we have a smart solar power collector and its individual objectives that branch off of this project. This system's objectives are to follow the sun's position and increase efficiency, move by calculations in the programming inputted from 4 calibrated sensors, and will minimize space used due to its design.
This is the design level 0 diagram. The system receives 1 input of sunlight and produces 1 output, which is the electricity generated.
The figure on slide 18 is the design level 1. This displays the interactions between devices within the system. Sunlight levels are monitored by the photovoltaic sensors inputted into the Distech controller. The Distech controller calculates the direction of sunlight using resistance values of the 4 sensors in pairs. The solar panels send data to the charge controller regarding collection status. The solar panels charge the battery bank. The battery bank supplies power to the LED lights to display power being present.
This is our control flowchart. It breaks down the sequence in which the system operates. The control device will initiate on power on. The device will move to the first initial position. The device then determines the elevation and azimuth averages and then moves for 2 seconds. The panel will then be moved in the corresponding direction. This process is repeated over and over to follow the desired direction.
The work breakdown structure is used to map out the activities and all of the details for completing each activity.
This is our Gantt chart. Ordering was yellow due to making our design larger. Hardware were delayed due to ordering. To test the Distech controller, we needed the new components. And the hardware and software test was delayed due to ordering the new components.
We used a 5-part management system to deploy a production version of our prototype. This involved a site survey to determine the best location for constructing the system. Design and purchasing process, component installation, controls that will benefit the system and the operator, and closeout involving inspections and certifications were done.
This slide displays our hardware components that were purchased for the construction of the system. Among these items are two 25-watt solar panels, an industrial umbrella stand used for the base for the structure, and two actuator motors rated at a max torque value of 180 inch-pounds.
Here we have the cost analysis table, which contains details of each component used, as well as the cost and the link for each piece of hardware. Our total has added up to $1,596.99.
The picture on the left displays the PV sensor leads being coiled around the input wire and added flux to the connector for equal heat transfer. The picture on the right displays the soldered connection of the PV sensor to the wire.
These pictures display the testing of a PV sensor in the dark and in the light to show resistance values on the multimeter. This test was done to each PV sensor for quality control testing.
This picture displays the testing of a PV sensor in direct sunlight. In the finished system, these sensors will input resistance from each corner and average out with motor movement toward the light source.
This design was created to offset the direct light experienced outside, which could create confusion within the program's averages. Each tube is offset at 15 degrees away from the center of the panels to provide a more accurate reading from each sensor.
Calculations for solar panel movement determine which direction the solar panel needs to move to equalize resistant values at a lowest possible value. That indicates that the panel has found the sun. A delay timer is used to restrict movement to a set number of seconds before waiting another set number of seconds before movement is allowed.
These pictures display the offset tubes, which angle away from the center of the panels at 15 degrees.
The design of this system was made in mind of having a wide base for stability in all directions, two actuator motors for optimized panel positioning on the X and Y axis, active sunlight tracking using 4 photoresistors, a timer to allow methodical movement of the motors, 50 watt-hours of solar collection capability, and a battery charger that is capable of 100 watt-hours charge capacity.
The left picture displays the rear of the entire system, while the right picture displays the front of the system.
The Distech EC-GFX is the program software used to program the automatic solar collector. GFX provides a customizable block-oriented programming environment to visualize the program values in real-time debugging. This is very beneficial during the troubleshooting and testing of the program for the system.
These logic options are the basic options that allow us to control our desired inputs and outputs. The basic control of our system is impacted by simple gates in a complex implementation. Inputs in GFX are color-coded in green. Outputs are color-coded in blue. Inputs and outputs can be configured in GFX to be analog or digital and display the desired values. For the inputs in this program, we are displaying resistance, and the outputs are configured to display a percentage of 0 to 100 and supplies a 2 to 10 volt signal to the actuator motors.
These blocks are used for advanced control features such as adding and subtracting or taking two inputs and averaging them. This allows us flexibility to control variables based on the input and outputs from basic logic gates.
These blocks are advanced state logic that allows us to fine-tune and select information that is going to be put into our logic program. This image is a screenshot of the x-axis portion of the GFX program. Details of the functionality in this program are covered. This image is a screenshot of the y-axis portion of the GFX program. Details are also located in slide 39 through 47.
Our custom timer functions as an on or off timer for when the panels are allowed to move. The panels are allowed to move in between the 3 and 5 second mark, and when reaching the 5 second mark, it resets the value to 0 and starts the count again. This feature allows us to change the time for which we want the panel to move. If we want it to move quicker or more frequently, we can lower the number down lower than 5 seconds. If we want it to happen less frequently, as we had before in our prior testing, we had it set between 10 and 12 seconds. This allowed the panel to move more methodically so that we could watch its movement as the test proceeded.
In week 3, we made a basic demonstration of the GFX program on YouTube. The link is available on this slide. In this video, it demonstrates inputs and output calculations as well as an active functioning of the timer and photovoltaic sensors.
In our logic flowchart, the items in green on the far left are our hardware inputs. The input values are of the resistance of the photoresistors. These values are averaged in the average block in the middle that are brown. Those averages are then moved to the add and subtract blocks and also to the timer blocks. We then allow the timer to pass the values through a switch within the allotted 2 seconds. These values are allowed to pass the timer and are set to the respective greater than, less than, and or block. A set point is also added to the add and subtract to separate values and give some room for error. The less than and greater than blocks will throw a true or false based on the logic sequence. When the two opposing logic gates are the same, such as east is greater and west is less than, and they are both true, then the OR statement is true for those two, resulting in the panel will move toward the east. Based on which OR gate is true, a timer will go up or down based in seconds. The timers whose value has changed will then go to the multiplexer. The output from the timer 1 or timer 2, as long as the variable meets the constraints of the limit gate, it is passed to the x-axis hardware output. The hardware output is then sent to the actuator motor that is associated with it. That variable is then sent to the timers for the next round of movements.
When we began our capstone class, we were planning on building a wind turbine and solar panel hybrid. It was deemed to be too technical for the 3-month timeline for our class, so we focused on the solar portion of this project. A 2-axis smart solar panel was decided on to maintain the active moving parts in this design. This was modified from the traditional utility use solar panels that follow the sun on one axis. A 2-axis system was found to be more efficient in tracking the sun's position in all times of the year versus the peak months in a year when the sun's position is optimal for the 1-axis models. If we were to build this again, we would use metal components for the weight-bearing features of the structure. This would alleviate stress that was found in the structure during our test fitting. We would also build a tray that holds the solar panels in aluminum C-channel to hold the panels in position more snugly. This project has been insightful and a well-deserved learning experience. Building the system again would prove to be more efficient due to our understanding gained from Capstone 1 and 2.
In Capstone 2, our objectives were complete the design phase, implementation of our program, executing hardware changes and individual testing of each component, and finally, building our prototype. Our plan was successful, and we are excited to continue testing our prototype as we collect data and demonstrate its efficiencies. Finally, we have provided links to the posted YouTube videos, demonstration, and actuator motor full range testing, and the actuator motor override to stow position and releasing to program control. When proper weather conditions return to San Diego, we will resume testing and create more time-lapse videos of our system doing what it was designed to do. Thank you.